Let's start. The talk is titled Exploring Malicious Windows Drivers. And so before I start digging into the topic, I wanted to give a shout out to people who actually did quite a lot of work before I did some of the work. I've been in the industry for quite a long time, and the more you spend in the security industry on the threat research side as well, you kind of learn how much you don't really know, and there are always new topics, even if they all sound quite old, there are always new areas in those old topics. And so this is the story about the drivers. So I've been working with Cisco Talos, which is Cisco's threat intelligence organization, for about 7 years, but before that I spent a lot of time in threat research organization, and I'm somewhere between Zagreb and Istria throughout the year. And so here's how I kind of imagine to kind of go to talk through 5 distinct, let's say, areas where we will really have a super high level to medium introduction into the Windows architecture and what's required from us when we look at the drivers, roughly what we need to know, but there's so much more about it as well. Then I'll talk a little bit about the basics of the drivers, the vulnerabilities, which seem to be very important now, and they are quite exploited by the threat actors. Then I look at some of the examples of the threats which I managed to find over the last couple of months, but also some of the well-known examples of well-known threat actors using and abusing drivers. So that's it. And then at the end is some kind of conclusion, but the conclusion is not that important, I think. So let's start and digging into the internals of Windows. Well, the most important thing to realize is that we have there are privilege rings in the x86 or 64 processors, which allows us to separate the so-called privileges, which kind of areas are we allowed to access, what kind of code we can execute. And basically they are distinctly, although there are 4 different privilege levels, it's been kind of custom that the 2 privilege levels are used. One, which is so-called ring 3, or there are rings of privileges, and ring 0. Every process that we create, whenever we run any program on Windows, it will run as a user with its own security token in ring 3, but the kernel will provide the services to the program, and it will allow it to actually conduct all of the functionality that's required, most of the functionality. So that was the high level, but then there's always a complication with Windows, and with the introduction of the hardware mode virtualization or hardware virtualization, we can also have an additional layer, which will be in the hypervisor or the hypervisor context, and we'll see that this is actually quite important for some of the security features that are included in Windows and possibly other operating systems, but we're looking at Windows this time. So looking only at the kernel mode, there is the kernel is kind of monolithic, but let's say there are different modules within the kernel. There are different logical parts of the kernel. The most important part is probably the executive, which basically takes every thread and then make sure that every thread runs an appropriate amount of time, and then it services various interrupt routines coming from hardware and software and so on. But there are also various managers for different objects. So we have registry, we have files, we have processes. Every object that we create in user mode, when we work with some of the resources in Windows, will have its own equivalent, its own data structure in kernel mode. So if you think about the process, we always think about it as a kind of one executable, but in fact the process is just a memory space, and in that memory space has its description in the kernel mode, in the kernel memory. It has its own structure, and that structure describes which memory is used, what's the main executable module, what are the objects that were created, every time you open a file you get a handle back. And there are actually threads, which are the main units of execution in Windows. So a process doesn't execute, it just describes memory space, but the threads are executing, and so every time you launch a process, there will be at least one thread of execution in that process. So if you look at this structure in memory in the kernel, there's the structure called _e process. Underscore just means that it's not really super well documented, or at least it's used internally in the kernel mode. And then you can see that there are like various interesting things, like a primary access token, which is the security that kind of assigns a certain abilities to access certain parts of the system for that particular process, like which kind of user and what that user can do. There's also a list of the threads that are there, like the list of threads that are owned by the process, and then there's also a list of additional processes. So this there's a linked list that allows us to traverse it and to see from our own process, if we find this e-process structure for our process, then we can find all of the other processes in the system. So this is just the idea, just to see like the process has one, thread has one, like almost any object we create in the user mode will have its own equivalent in kernel mode, which is maintained by the kernel, and it's kind of a little bit difficult for us to access it directly. So we only access it through Windows API, for example. So the other very important idea of not just Windows but most of the modern operating systems, that each process is run with its own virtual memory space, and each process thinks that it has basically a flat memory space which they can be addressed. But there are operating system structures, the page tables, which basically you can have two same virtual addresses in two different processes, but they will point to different parts of the actual physical memory. So even if we have two virtual memories that appear exactly the same, then in physical memory those bits are placed everywhere around. So kernel is very important to maintain this transition or translation between the virtual memory that process things and works within to the actual physical memory, and this is like one of the parts where some of the vulnerabilities are seen. So this is just to show, like at the top we have the linear address, which is what is called the virtual address. The memory addressing from 48 bits are used in 64-bit Windows for memory addressing for the processes, and then there's a special register called control register 3, which is part of the CPU, and that register points to the first layer of the translation tables. So we have 4 layers of indirection of the translation tables, which then somehow and magically translate the virtual address into the physical address. And so you can see that when the processor makes a transition from one thread to the other, if the thread is in a different process, then this value of the control register 3 will be different. So every process will have its own set of page tables, and therefore that allows us to translate the same linear address to different physical addresses for different processes. So like I mentioned, in the Windows world, most of the things we do use it by using Windows API, and there are different levels of Windows API. So for example, here we will have an ability to open process. So there is a function in kernel 32.dll which allows us to open process, so we can read from the other process space or write to it if we have the permission to do it. But then what really happens when we call that function or the API call, it's not executed in kernel 32.dll, which firmly stands within the user mode memory of the process. It then calls another function in kernel base.dll, which is one layer below the kernel 32, and then the last layer is in the library called ntdll.dll, which is the lowest level of what we have in user mode, and there simply the transition to the kernel mode happens. And so then, if we want to actually open the process, you remember that we have to create all these structures in memory. We have to create the kernel object in the kernel space as well. And so now we start executing open process call, but within the context of the kernel. And the first function that's called is KI system call 64 or something like that. And then it goes through the other system where it eventually executes anti-open process in anti-OS kernel.exe. So it's quite a complex path when we just try to open a process. From our point of view as programmers, we simply call open process, but there are so many things that happen below. And so if you look at the kind of reverse the code, the question is, when you make a transition from the user mode to the kernel mode, how does the kernel know where to start executing? And so the answer to that is that the processor also has a number of what is called model-specific registers. Those are just like memory locations on the processors that they will keep adding. And somehow one of the processor is called, I think, L star something. It's a number C00082 on 64-bit Windows, and that actually contains a pointer to the place where the code will start executing in kernel mode. So here we see the disassembly of the create file function. So what the create file function, and that function is identity.dll.dll. That's in top left. So it just puts a number for the call in the register EAX, so 52H, and then it calls the syscall function. And that syscall function then the processor traps and makes a transition, and then looks at the address in the model specific register, which has always you can always use it by number, but it has its own like names, and depending on so this is the name is MSR, model specific register L star. So L star, there are different model specific registers used for memory management, for power management, for fan speed. You can use it to read certain things about the processor and the state of the system. But what we are concentrating here are mostly the model specific register, which point to where the kernel will start execution when the system call happens. So, so that's super really high level, and that's what's required from us to kind of understand and work with the drivers and driver vulnerabilities. So now I will transition into like the introduction into the drivers. So drivers is like looking at the drivers on the disk. It's just like standard executable file, but it's a library, and its feature is that it has a native flag as well. Usually has a .sys extension, and it basically it's created so that the kernel functionality can be extended in some ways. Sometimes it's to support your graphic card or whatever is required to support, but the interesting thing is that you can also create purely software drivers which add some additional functionality to the kernel. Like the good example will be antivirus, endpoint detection, response tools, and so on that provide some additional functionality. I think everybody is aware of CrowdStrike's driver. Yeah, CrowdStrike driver really works well. So the issue with the kernel is it's a very sensitive part of the operating system, and so you have exactly the same abilities. So you can do anything what the proper Microsoft kernel can do once when you have a kernel mode driver loaded, and that's why, unsurprisingly, for the malicious actors and threat actors, it's very important for them, or they will try, if they can, to reach this level of privileges and to try to integrate with the kernel, because once you have the code running in the kernel, you can do all sorts of things. Like, what can they do? Well, we'll see later in some of the examples that we'll try to do. So typically the driver is loaded through either inf file, which is then describe how the kernel should load it, or creating, there is a load driver ntdll as well function, which you can use if you have the privileges to run it. And you can also create a driver service and then run it through the service control manager or start the driver service as well. So there are like different ways. And the similar way as any executable files, we have certain entry points into the code of the driver. So the driver entry is the function which is called immediately, but the driver needs to create certain objects in memory. It has to create the driver object. Remember that we had the process object for the kernel, but when the driver is loading, it has to also, kernel needs to create the driver object. So there's a call to create the driver object, there's a call to create a device object, which will be receive the request. And then there are different routines that the driver needs to define. So there will be a driver init, so initialization routine, and there will be some other, but we will be specifically focused on one routine which allows the user mode functions or user mode code to communicate with the driver. So how does the driver communicate with the user mode function can communicate with the driver, but also kernel code can communicate with the driver. The main form of communication is something called I/O request packet, which is again a structure, and that structure encapsulates everything that's required for one or more drivers to process this the code that's the function that's required from the driver, but also the parameters that were given to the drivers. So and the function that we will be mostly interested in is this ERP MJ device control function, which allows the driver to define its own control codes, also called IOCTLs or IOCTLs. And so a function in user space can call this device IO control function from the user mode and put specific value in it, and then an IR request packet is created, sent to the driver with that code, the IO control code and the parameters as well. So how do you connect to the driver? First, you actually call create file, and you create file with a symbolic link to the driver device, which is created by the driver itself. And once when you have that, then you can use it to send various functions to the driver. So on the left, we have the user mode function, and then on the right, we have the kernel mode function. Kernel mode is the driver, and the user mode is our own function which sends those I/O control code. So just to reiterate, on the left, the function we are interested in is device I/O control. On the right, on the kernel side, we have registered this kind of function callback, which will then be called by the kernel once when the request reaches the appropriate driver that we are interested in. The drivers, like other objects in Windows, also have the access control list, and you can define it in security data description language, and basically that means that some of the driver functions can be called by certain users. So you can imagine that administrators will be able to call some of the driver functions. But there's also a specification for the world, so for any user on the system to call the driver. And since the drivers are very, very complex pieces of code, and there are actually not that many, are there many driver programmers here? Anybody programming drivers? You see? It's kind of interesting that none of us are really kind of programming drivers, because it's a very specific and specialized part of writing. So you can imagine that the pool of knowledge is kind of high, but there is very few people that know how to properly do it, and as a consequence of that, there is a huge amount of wrongly programmed drivers. And so here we have a statistic by Trend Micro, which shows just how many drivers Microsoft revoked by certificates, by year, and some of them that were detected by the anti-malware vendors. And you can see that we talk about thousands, if not tens of thousands of drivers, which either have some vulnerability or they already contain malicious code and they execute this malicious thing. So over time, it seems that their usage only grows, and so there is luckily, when the usage of something grows, it also prompts Microsoft to introduce some of the security features which we'll see later. parameters. There's also an interesting project called LOL drivers, so living on the land drivers, which lists and adds new vulnerable drivers as they are developed. So from the idea of these living on the land drivers comes also the notion of so-called bring your own vulnerable driver, BOYD, where the threats are actually taking some of those drivers, and Windows basically, for every new driver you create in Windows, there are really stringent request on, you need to certify, you need to sign the driver digitally, but also Microsoft has to sign the driver digitally. So it's very difficult now for new drivers to be like completely malicious. So what's left to malicious actors is to load so-called legacy drivers. And legacy drivers will still be loaded by Windows unless you kind of completely remove that functionality by default. So there is still thousands of drivers which can be loaded and be part of the kernel, and those drivers contain some of the weaknesses that we'll talk about. The first weakness we will talk about is, remember that we talked about those model-specific registers. So there are some drivers, and mostly the drivers we have like vendors of PC vendors, Asus, Dell. They create these utilities for updating BIOS, updating certain functions of the hardware and stuff. So they usually have the drivers, and as you can imagine, those drivers are not always the most perfect. And so some of the drivers don't even ask what user you are, and then allow you to do something. So the issue number one is allowing you to write into the model-specific registers of the processor. So from the user mode, you can basically say, if I know that I can pass some kind of buffer, and I change that L star register, which will tell me when I execute a call to the kernel where the code will start. If I can replace somehow that call, then the game is over. I have my kernel mode execution. So a long time ago, you could basically change the model-specific register to jump into your own code, and that code was the memory that was allocated in user space. And then Microsoft came with a supervisor mode execution prevention, which then prevents you to do that. So the game is always the threat actors do something, Microsoft does something else to prevent this. So here is one of the driver called WinRing 0. It's part of the open hardware monitoring software, which every time you use any crypto miner, well, malware or software, XMRing is not malware, but it's used by many malicious actors. That code is basically by default simply just changing some of the memory-specific register, which allows the higher speed of mining for Monero, for example. So if you have hardware memory prefetch, apparently that's bad for the processor speed, so therefore they disable it by default. But that driver can also be used to change any of the model-specific register, read or write. It also contains some code to read or write specific parts of memory. The big issue number two is that the drivers expose functionality which allow the user mode process to read or write virtual or physical memory. So this is the different things. Here in the model-specific registers, we can basically change just a pointer, like 8 bytes or whatever. But now there are also some drivers which simply allow you to call them and copy from any place to any place. So if you know certain parts of the kernel memory, you can simply intercept some of the codes, place your own code there, and then achieve execution in kernel mode. So this is an example of an anti-cheat tool, Echo Anti-Cheat, from 2023, where they kind of tried to shield some of the memory write function, but the way to attack it, you authorize your process so that it can write to the memory by calling one input-output device, like the call for the driver, and then you simply issue another one, and you just kind of overwrite any parts of the kernel memory. So this anti-cheat software is like for several different games, Rust, Roblox, and few of the other ones still quite popular. So here we see the first we authorize our process by issuing this device IO control code 6224 something, and then once when you send the code, then basically it allows you to copy memory, which is like just down below. The third big issue is what we would classify as misusing the existing driver functionality. So not just the reading and writing of memory or register, but some drivers, hint anti-malware drivers, can expose some functionality which can allow bad guys to do something. So in this case, the big example I have is another anti-cheat driver, an old Capcom driver, which basically allowed the user to call it, to send the buffer to it, and then the buffer would be executed in memory. So it's not a bug, it's a feature. So this is what happens first is you send this call, and there are a couple of function calls. The first function call is to change the control register 4 and to allow the non-signed code to run, and then to call your own function, and then to reset this control register 4. But it's kind of a bit technical. So let's think about like what are the typical payloads we've seen in the threat actors using or abusing the drivers. So we would have local privilege escalation, which allows our process, which we created, some new user mode process, to achieve something which was not planned for that process or not allowed by that user. We can terminate various security tools. We can terminate various anti-cheat programs that kind of try to prevent cheats in various games. And we can then use these functionalities to create our own loaders to load other unsigned drivers, which will then contain the main functionality, the rootkit, for example, that will then hide processes, hide malicious files, hide network connections, and so on. So the first relatively simple example is this privilege escalation. Probably the most common ways that these threat actors and some of the loaders are doing it, they load their own copy of Windows kernel, so NT-OS kernel, in the user mode, and then they look for the export. So there are certain exports that the DLL or the function can, the file will export, so you can basically import it in your program and then use it to call those areas. And in this case, an interesting area is this called PS initial system process, which is not export of the function, but it's an export of the location of the virtual address in memory, where the first e-process structure is placed when the system boots. So you can use another relatively undocumented but well-known function called NT-query system information to get the NT-OS kernel base virtual address, and then we know the offset, and then we read this data using the driver. We find the pointer to the initial system process, and now that we have the pointer to the first structure, then we can use the linked list to traverse to our own process, and then simply copy the token or the access token from the system process to our own process. So here we can see we have the list of processes, then we kind of find our own. But first, the process we found is the one with the ID 4, which is the system process. And then we traverse the list to find our own process. And here we also have the token, the primary access security token, and we just copy that structure from the area of the system process into our own process. And somehow by magic, our process also has the same privileges as the system process. So that's the privilege escalation. The second example is, I mentioned like disabling endpoint detection response and anti-malware software. I recently looked at this example. I tried to find or hunt on VirusTotal for the newest examples of the drivers, and then I realized that there's this Chinese executable, or like, it's literally in Chinese language, that's created to look like OneNote or some other executables. And what it does is, initially it drops 3 files. The top file, for some reason called 3.exe, is a zip file actually. There's a file that suspiciously sounds like an official operating system file called anti-handle callback.exe. And the driver dbutil2.3, which is the Dell driver, a vulnerable driver that allows us to write physical memory. And then it drops, the next layer is where the zip file contains additional layers of code. The first one is the edr.exe, which is the real blinding EDR tool, which can kind of prevent any EDR, most of the EDRs from working. And then that kind of anti-handle callback also loads a library called irlicht.dll, which has an export to decrypt this server.log. Server.log is not the actual log, but it's an encrypted file. That file is decrypted, and then the final payload is pushed into memory, and the final payload is Ghost Rat, which is quite an old remote access tool, but still used by mostly like threat actors from China. So the real blinding EDR is just one of the EDR silencing tools. So what it does the way you officially use, or you can monitor what's happening on the system, is that kernel provides to the anti-malware software a number of callback function which you can register. So every time when a registry changes, when a file is accessed, when any object is opened on the system, when the new process is created, when the new thread is created, and when the new DLL is loaded in memory, the anti-malware software gets this callback with the data of what actually happened. So what most of these tools do is they try to find these structures in kernel memory, and then they overwrite it kind of with zeros so that the EDR can still run. And you think that everything is normal, but no events are received by the EDR software, and therefore you have no visibility what's happening on the system. So this is not the only one. The EDR, there is a number of those. Real blinding is not the only one. So if you like, I can share the slides, and happy to look at for that. So here's exactly the same thing. This was discovered by Avast, I think. Where we have the APT, so the North Korean threat actors. Lazarus is the kind of common name for all the groups that come from North Korea. And so they do exactly the same. They load this dbutil Dell BIOS utility driver and then use it to overwrite the callbacks for the kernel. So the inspiration for the tools that are now open source tools usually comes from the advanced persistent threat groups, which discover these vulnerabilities kind of more or less first. They start to use it, and then slowly it's trickled down to the most like of the commodity actors. So the other things that we mentioned, these are the tools that allow you to load your own unsigned drivers to memory by exploiting those vulnerable drivers. And one of those, which I kind of managed to, let's say, find, was a cheat driver or anti-cheat. The name was sexygirladdy.exe, and so I thought that must be malware. But it turns out it's just the anti-cheat. And so it's based on this Lenovo mapper that tries to exploit one of the vulnerables Lenovo driver to kind of prevent some of the code. And what it actually, finally what it does when it's managed to load this driver, it tries to bypass the TPM check for the license of some of the games. So otherwise, when the hardware ID is checked for some reason for some games, and then this tries to bypass that check in the end. So I had no idea like what do these do. I usually look at the threads, not at the cheat, but when I started looking at it, I was like must be, and then I realized it's this bypass. So other well-known examples of misusing the driver functionality comes from the well-known APT attacks, like different Vipers, for example, like Shamoon that attacked Saudi Arabian oil facilities in 2000. In few instances, there are like few versions of it. Initially used a raw disk driver from an official product and load it and simply allowed it to overwrite portions or pieces of the hard drive and kind of wipe the hard drive. A recent example is a hermetic Viper, which was attributed, I think, to Sandworm Group, which operates acts with the interest of the kind of Russian political interest in Ukraine. And so here we just see a dump of the resource segment of the file where we have various versions of the driver they were using. So we have 64-bit, 32-bit of the driver, and the ones that also support Windows XP, because we know that there are many old versions of Windows used in countries probably such as ours as well. Here's an example from Trend Micro that basically abuses another anti-malware software from Italian anti-malware company VirIT. And so that basically allowed simply to load that driver. If the driver is loaded in memory, you can call one of those device I/O control codes, and that will simply terminate any process you like. Because as a part of the cleanup of malware, most of the anti-malware software also needs to have this ability to terminate malicious processes. So here we had the fact that the VirIT guys were not aware that need to set proper access control, and so you can call it from any other user or any other software, which was obviously like a mistake. And then finally, this example from which was fixed in February 2024 of the vulnerabilities is, we talked about bringing your own vulnerable driver, but what about having the proper leaving of the land? So what if you can exploit a proper Microsoft driver which is loaded with every single piece of Windows? That's kind of like almost a holy grail for exploitation. And here we had again example of the Lazarus thread group, which discovered that the app locker, which is the feature in Windows that allows you to block or allow certain applications to run, have a function for creating some specific smart checksum of the file, which also allows the caller of that function to supply 2 pointers, and those 2 pointers can then point to any code which will then be called back by the kernel. So this was discovered, I think, also by Avast in October or earlier in 2023. But then they contacted Microsoft. Microsoft was first not very open to fixing this issue, because apparently you need to have local service privileges, which obviously is very easy to obtain. So they didn't say it's admin to kernel, it's local service to kernel, but it's still a serious vulnerability which was exploited by Lazarus. And eventually, when they realized it was exploited in the wild, they fixed it in February 2024, and they fixed it by making sure that the call is only coming from kernel mode, not from the user mode. So you couldn't call this function for checksumming from the user mode. So what was I failed, I think, to mention that the payload for most of the time in Lazarus is this rootkit that tries to, from the user mode, hide some of the presence on the system. So the main goal for the driver is to set a flag in a k-thread structure that then shows like the previous call came from kernel mode, which somehow allows the user mode code to call functions for reading and writing kernel memory. So finally, the final sections are the Windows mitigations. So it started very early with the XP Service Pack 3 with PatchGuard. PatchGuard was improved over time, and PatchGuard just every, I don't know, few hundred milliseconds, I don't know really the frequency, scans certain areas in kernel memory to make sure they're not patched by malware. And so it can be defeated because you can do it faster than that when it comes back. Then the second feature is that all drivers must be digitally signed, and we know that, and we kind of now all the Windows versions are signed. And then slowly, kind of there are more and more mitigations which were added to the Windows. So to mitigate the bad drivers like the new rootkits, they require new Windows drivers to be signed by Microsoft, which we already mentioned, which obviously makes it much more difficult to create malicious drivers. Then the supervisor mode execution prevention and access prevention prevents the user mode to send the buffer, to show the buffer in user mode and then call it from the kernel side. Then we have the address space layout randomization, which obviously makes it more difficult to find certain structures in memory. Then we had the virtual address shadow, which was shadowing, kernel virtual address shadowing, which was created to prevent meltdown exploitation some time ago in 2019, I think. But also is a security feature. Then we have the control flow guard, and I think I'm going to mention the Intel's control flows enforcement technology that creates like a shadow stack in memory. Kost will talk a little bit more about that tomorrow. In more depth, but more on Linux. Yeah. Okay, so if you're interested in this enhancement technology, which basically prevents overwriting of the stack and ROP payloads on the stack. And then maybe finally, and quite important, is this kind of Windows virtualization-based security, which basically has this additional layer, the hypervisor layer below the actual Windows operating system. So the operating system runs, the kernel runs, it thinks that it talks to the physical memory, but one layer below it, an additional layer of address translation, basically allows any accesses to some physical parts of the memory for the let's say virtual machine within the hypervisor to be trapped, and then basically things such as credential guard, which disallows reading of the credentials from memory, is based on this technology. But also can prevent loading of bad or loading of the vulnerable and legacy drivers. So the evolution of threats versus mitigations, like probably 15 years ago, we had these kernel mode rootkits, which will just simply load and execute from the kernel, and then Microsoft came out, okay, now you need to sign all of the drivers. The next phase was where we had this direct kernel object modification rootkits and bootkits, which then created the trusted boot from the Microsoft side. So you can see that the threats are basically driving the adding of the new security features to the Windows operating system. And now we have this exploitation to load your own driver, and then the virtualization-based security is the answer to that. So this brings us finally to the conclusion of the talk. We went through the introduction of Windows. We went through the long path of trying to understand the drivers, to the issues with the vulnerable drivers, the payloads, and actually finally the mitigations. So the result of everything is that today's Windows 11, if you turn on all of the security features, makes it almost, I wouldn't say impossible, it's never impossible, but extremely difficult to exploit drivers and introduce your own kernel mode code with Windows. And there are certain steps if you kind of not willing to include all of these features, because every security features will also have a performance impact to your Windows operating systems. So not all of the systems will be able to afford that. But then there are things such as the Windows Defender application control blacklist or block list, sorry, which basically lists all of the known vulnerable drivers and will prevent them from loading. You can also set up that only the drivers signed by Microsoft are loaded in memory, which also really limits the attack surface a lot. And for threat hunting, you can use like sysmon to monitor or maybe some of your EDR tools to monitor when a new driver is being loaded in memory, so you can go back if some bad activity has been discovered. So with that, I would like to thank you for listening, for being patient, and I wish you definitely all the best for the rest of the conference. It certainly sounds like it's going to be very interesting and entertaining. Thank you. Perhaps we have time for a question or two.
So thank you. And during the talk, you mentioned a couple of these examples of malicious attempts of attack coming basically from, I guess, Eastern Bloc, like China and Russia, and also the Lazarus from North Korea. Sorry.
Yep.
Have you, during your career, ever encountered these types of attacks, but coming the other way around, like from the Western side to the Eastern?
So now it's a political answer I need to do. I personally haven't, but certainly there are research organizations which are well versed. I mean, for example, one of the examples is the Shadow Brokers leak, which is attributed to NSA, right? It contains a kernel mode exploit, what is it called, blue something, eternal something, right? So definitely you can count that the other side is also looking at drivers, and they won't burn the vulnerability unless it's targeted to a specific and well-known, and it can influence the cause of political actions on the other side, I think, and it's kind of... Stuxnet. Exactly, Stuxnet was one of them, but I don't know if Stuxnet will actually use the drivers. Yeah, so there are always examples, and you can count on them. So, and it's the most likely is that, let's say, the Western countries or organization will provide public information about the other side and vice versa. So if you follow, for example, Kaspersky's, they're more likely to document some of the actions of the other side.
Thank you.
Any more questions?
So the mitigations that Windows introduced, can you choose which ones you turn on and off? Can you turn off SMAP or CET, or is it all decided by default on boot?
As far as I know, with each new version and sometimes each new release, there will be new features included by default. And then you can, by using some group policy, you can enable some others as well. But I think, as far as I know, not all of them will be in Windows 11 by default, but a lot of them would.
Okay, thank you.
Anyone else? Okay.
Thank you. Very interesting, but the question has nothing to do with malware. What's the future of Cisco Taos?
Okay.
Do you feel threat?
So this refers to some news which were
Yeah. This week layoffs.
which were
to be
real,
honest, yeah.
which were real news, which refers to the fact that as a part of the restructuring, certain number of members, and including our vice president, was laid off by Cisco. We are very disappointed by that internally, I have to say. Our VP was there for 20 years. He was a really great guy. Still is a great guy. We are considering various options, but most likely we will continue the way where we are, knowing what will happen. Somebody will step up from the existing leadership to lead Talos, but the future will show.
Yep. Okay. Last question.
With more and more, with gaming becoming more and more a relevant part of the industry and a general value-added processes in our society, more and more companies are going to kernel-level anti-cheat. Do you have any opinions on the implementations they do? Because let's say games are not famous for having the most solid code base.
I agree with you. In fact, we can compare the anti-cheat kernel drivers to the anti-malware kernel drivers to a point. The reason why most of the companies will have kernel drivers from the anti-malware side primarily is that the kernel before didn't have enough functionality exposed to allow for proper, and also you want to isolate your good code from the user mode code, right? So the user mode code makes it more difficult to remove it. Microsoft used the CrowdStrike vulnerability, the CrowdStrike bug, not vulnerability, to try to enforce more, to move the drivers outside of the kernel as much as possible. And last week there was a Windows driver or something summit, or Windows anti-malware summit in Microsoft, and they kind of hinted that they want less and less functionality to be in the kernel and less driver functionality in the kernel. So that can apply to anti-cheat as well.
I was asking about the implementations you have seen, because I assume you've seen a driver or two in your career. Would you consider them generally well written, generally sloppy written? Because
I kind of mostly looked at most of the malicious driver and those like vulnerable drivers, and they're pretty old and not that well written. I didn't look at that many anti-cheat drivers. The old ones are quite bad, but I hope that functionality improved. I certainly think so.
Okay, thank you. Can we have another applause for Vanja?
Thank you.